Hi students, good morning. Welcome back to our physics classes. Today we are going to start with the other version of optics. We have already finished with the ray optics, in which the light is considered as light rays. And with the concept of ray optics, we have seen refraction happening from a spherical surface and a prism, and we have seen some optical instruments also. Now we are shifting our focus from ray optics to another aspect of light, that is wave theory of light. So wave theory says that light is emitted or absorbed. Simply, light is transmitted in the form of waves. In the form of waves. Actually, this theory was given by Christian Huygens. So Huygens wave theory says that light is transmitted in the form of waves. And as light wave travel from one medium to another, it will not make any changes in the medium. It will not make any changes in the medium. I mean, in the sense we can say that light wave is a transverse wave which is traveling through a medium. In the sense, Huygens described light wave, or described light. Later, it was found that de Broglie came and said that it is not a particle, light is not a particle, and light is not a wave, but it can show both the properties. So it comes a dual nature of matter, then dual nature of light, and hence it is extended into dual nature of matter. That is de Broglie concept. And finally, James Clerk Maxwell suggested that light is a wave and it is generated from accelerated charges, which is light is an electromagnetic wave. So electromagnetic wave theory is a widely accepted theory about light. Regarding light, the first theory was given by Isaac Newton, and Isaac Newton said that this light is transmitted in the form of small balls, and these balls he called as corpuscles. That is known as the corpuscular theory of light. That is a particle nature. Then, when our Heisenberg came with the uncertainty principle, based on that, our Christian Huygens said that light is not a particle, it is a wave. And later, de Broglie incorporated both. And in between, another theory came regarding quantum theory of light. Max Planck quantum theory of light. Quantum theory is strictly based on dual nature. That means it is in the form of particle, as well as that particle will act as a wave. That we will discuss in photoelectric effect and modern physics. That section we will discuss about that. Anyhow, that is another theory regarding the light, that is quantum theory of light. Light is transmitted in the form of small packets of energy, and each packet of energy is called photon. Then Maxwell's electromagnetic theory came. So the most widely and the most modern theory regarding light is our electromagnetic wave theory. But here we are not considering light as an electromagnetic wave, but we are merely saying that it is a wave. Light is a wave, and how wave is propagated, that is light wave is propagated, and based on wave nature of light, how we can express or how we can describe the properties of light, like reflection, refraction, all these matters we want to discuss here. Okay, so we can start with wave optics. Okay, so we can start with wave optics. See, as I already told you, the first statement we have to remember regarding the wave nature is, first term that we have to remember regarding the wave nature of light is wavefront. The term is wavefront. So what do you mean by wavefront? And actually the wavefront, the term came from Huygens wave theory of light. Christian Huygens wave theory of light. So we have to start with Huygens wave theory and wavefront. Huygens wave theory and wavefront. So wavefront is defined as locus of all points vibrating with the same phase when light wave is traveling through that medium. That is termed as wavefront. And I already told you, now we are not considering light as an electromagnetic wave. If you consider light as an electromagnetic wave, this wavefront concept cannot be explained in this way, because electromagnetic waves need no medium to travel through. So here Huygens considered the light is traveling through a medium and if you draw a surface in a medium, such that all the medium particles lying in the surface are in the same phase of oscillation, then that surface is called wavefront. In other words, it is the locus of all points vibrating the same phase when light wave is traveling through a medium. See, here in the diagram you can see two wavefronts in two shapes. In first one, it is a arc, and this arc is made from a sphere. So this can be considered as a spherical wavefront. It is a spherical wavefront, because if you have a point light source, from this light waves can travel in all possible directions. So that will derive a spherical wavefront. And here it is a plane wavefront. So when you consider a light source, from the light source only, and the nature of the shape of the wavefront depends upon the nature of the light source. If it is a point light source, we can have spherical wavefront. If you are having a slit, suppose if you are having a slit, just like a slit is there, through this light can pass through, so it can act as a light source. So from here you will get a cylindrical wavefront. See, that means from this light source, light waves can travel in all possible directions. So it derives a circle surrounding that slit, which means you will get a cylindrical wavefront then. And whether it is a cylindrical wavefront or a spherical wavefront, if you are considering a distance at infinite distance from the source, that means a very large distance from the source, the wavefront will be a plane wavefront. So wavefront is the locus of all points vibrating with the same phase when light is traveling through a medium. So spherical wavefront can be there, plane wavefront can be there, and cylindrical wavefront can be there. So these are the three different kinds of shapes of wavefronts. Okay, so Huygens wave theory says, and it is based on three statements. Huygens wave theory, actually it is not a single statement, it is based on three statements, and these three statements are called postulates of Huygens wave theory. So it says, what are the three statements that we have to see? Listen carefully. Every particle of the medium situated on the wavefront act as new wave source from which fresh waves originate. These waves are called secondary wavelets. Okay. So every point present in a wavefront can act as another source. Can you understand that statement? Every point in a wavefront can act as another source. Suppose here you have a light source. Here you have a light source. From this light source, spherical symmetry is there, and at any instant you are having a wavefront AB. You are having a wavefront AB. Okay. So this is a wavefront generated from this light source. Yes. This is a light source. Yes. And from this light source, a wavefront is generated as AB. AB is a wavefront generated at any instant. Suppose. See, there are different points A, B, C, D, E, F, G or that wavefront. And this AB you can consider as a primary wavefront. AB you can consider as a primary wavefront. See, from this primary wavefront, each point can act as another source. Each point can act as another source. What is the property of a source? From source, light wavefronts can be generated. See, as we already said that light is traveling in the form of waves, actually light is traveling in the form of wavefronts. As the light from the source, see, this is the light source. From the light source, as the waves are traveling, which means these wavefronts are growing in size. That is, the radius of this wavefront is increasing. Are you getting me? That is the mechanism of transmission of light wave. That means wavefronts are enlarging. As in the case here, what will happen? The cylindrical radius is increasing like that. Okay, so like that, as the light wave travels through, advances in a medium, the radius of wavefront increases. Okay, now suppose through this medium light is traveling with a velocity v, and suppose here you have a, suppose I am taking a plane wavefront here. This is a primary wavefront. Each point on this primary wavefront can act as another source. So you can predict where will be the next wavefront after a time t. After a time t, as the light wave is propagating, after a time t, this wavefront can, light wave can travel with a velocity v. So the distance traveled by light will be v into t. Okay, v into t. So to make the next wavefront after a time t, what to do is you have to make circles or spheres, not circles, spheres. In 2 dimension it is circle, but it is actually a sphere. From this point source, you can make a sphere whose radius will be this Vt. See, from each point from the wavefront, you can have such a spheres with the radius Vt. See, Vt, this from the point B, Vt, from the point C, Vt, and you join the tangent to all these spheres. You make a tangent touching all these spheres. That is A dash, B dash. That will be the next wavefront. Here in the spherical wavefront, as you see, from a spherical wavefront you can derive only another spherical wavefront, but its radius will be increasing. And a tangent drawn from the center of that sphere to the wavefront will act as a light ray. In the ray optics we have seen what is light ray. So this is the light ray, means the propagation, direction of propagation. This shows the direction of propagation that is perpendicular to the wavefront. So if you want to make another wavefront at a time t, that is A double dash, B double dash, what to do? A double dash, B double dash, you have to make. So far what to do? You keeping each point or the secondary wavefront. Now the secondary wavefront can act as a primary wavefront. From here you can make the circles with the radius Vt, and you can join the tangent to all these. That will provide you another wavefront. See, if you are making here, you will get another spherical wavefront here. That means the wavefront goes on increasing. The radius of the wavefront goes on increasing, or the wavefront is advancing as the light wave is traveling through a medium. So the first postulate is every particle of the medium situated on the wavefront act as a new wave source from which fresh waves originate. Here, fresh waves are originating, and these waves are called secondary wavelets. Second postulate is secondary wavelets travel in the medium in all directions with the speed of the original wave in the medium. So secondary wavelets can also travel with the same velocity. Then the envelope of the secondary wavelets in forward direction at any instant gives the new wavefront at that instant. Okay, so here you have to remember two terms, wavelets and wavefront. Wavelet is these spheres and the tangent to the wavelets are wavefronts. Tangent to the wavelets are the wavefronts. Okay, so remember those two terms, wavelets and wavefront. So these are the three postulates. First postulate is from every point on a primary wavefront, new wavelets can be generated. That wavelets are called secondary wavelet. Secondary wavelet travel in the medium in all directions with the same speed of the original wave, and envelope to the secondary wavelet in the forward direction at any instant give the new wavefront at that instant. So A dash B dash is the new wavefront, and this may be, suppose you can call it as CD. CD is the previous wavefront. Before A it was at CD. Now it is AB, and after time t it will be A dash B dash. That is the advancing of a wavefront. Okay, so that is the propagation of light in the form of waves according to the Huygens wave theory. Huygens wave theory says that every point in a primary wavefront can act as secondary sources. Secondary sources provide secondary wavelet. Secondary wavelet travels with the same velocity as that of the original wave, and the tangent to the secondary wavelets provides the secondary wavefront. That is the three postulates of Huygens wave theory. Now, based on this Huygens wave theory, we have to explain the process of the property of reflection and refraction. We have to describe the property of reflection and refraction. Remember, this reflection and refraction in wave theory, we are considering not the light rays but the light wave fronts. So the easiest wavefront is easiest way of expressing a light wave or dealing with a light wave is a plane wavefront. So we are taking a plane wavefront as the example, and using a plane wavefront we are describing reflection and refraction. So we can move on to reflection by reflection of light using the Huygens wave theory. Okay, see, this diagram shows reflection. See, S dash is a mirror. S dash is a surface which can reflect light. Here AB, see, this AB is a plane wavefront. AB is a plane wavefront. And in the medium, see, this is the first medium only. In reflection we don't care about the refractive index of the media because reflection happens in one medium itself. So AB is a plane wavefront which makes an angle I with the surface on which it is falling. That means on the mirror S dash. So this I can be taken as the angle of incidence. The wavefront makes an angle of incidence I with S dash. Okay. Now I already told you the line span normal to the wavefront can act as light ray. So here one arrow mark is shown. This is a light ray falling at the point A. At the point of incidence, N is a normal. See, incident light ray makes an angle I with the normal, that is angle of incidence. So from this point, you have to make another wavelet. So how you can make a wavelet here? You can make a wavelet here in such a way. Suppose V is the velocity of light in this medium. So light wave or light wavefront or the light ray travel with a velocity v through this medium. Already at the point A, light fallen on that surface S dash. But from the point B, that is on the same wavefront, from the point B, light ray didn't reach over the mirror. Light has to travel with a velocity v for a time t to reach from B to A dash. Okay, then only it can reflect from here. So during the time, suppose t is the time taken by the light ray to reach from B to the mirror, that is the point A dash. Okay, t is the time taken by the light ray B to reach on the mirror, then only it will be reflecting back. But already from A, light ray fallen on mirror. So what will happen? From A, already reflection takes place, but from B, it is again traveling in the forward direction to reach over the mirror S dash. So during the time t, the distance traveled from B to A dash will be Vt. So from the point A, taking the same Vt as the radius, you have to make an arc here. Then from this A dash, you make a tangent to this wavelet. From the point B, you are making a wavelet here with a radius Vt. From the point A also, you have to make a wavelet, and that is B dash. So tangent drawn between A dash and B dash, these two wavelets, A dash and B dash, will give you see the secondary wavefront. I already told you, Huygens already told you, tangent drawn to the secondary wavelets can provide you secondary wavefront. So this is a tangent drawn between those two wavefronts there. Wavelets there. This is one wavelet and this is another wavelet. So between those two wavelets, you have made a tangent. So that is A dash B dash. So A dash B dash is the reflected wavefront and AB is the incident wavefront. See here, this A dash B dash is a reflected wavefront, and this reflected wavefront makes an angle R with the mirror. So you have angle of incidence I and angle of reflection R. You have to prove that this diagram follows the law of reflection. What is law of reflection? Angle of incidence is equal to angle of reflection, that is I equal to R. That you have to show. For that, you have to you have to consider triangle AB A dash, that is AB A dash, in which B A dash will be Vt, B A dash will be Vt, and A dash will be A dash itself. See, sin I is equal to B A dash divided by A dash, and from the triangle A B dash A dash, A B dash A dash, sin R is equal to A B dash divided by A dash. Can you see that? Both. Then sin I by sin R is equal to B A dash divided by A dash multiplied by A dash by A B dash. A dash and A dash get cancels. B A dash divided by A B dash is remaining. That is Vt by Vt, which is equal to 1. That is sin I equal to sin R. If sin I is equal to sin R, you can say that I equal to R, which follows the law of reflection. So this shows this proves the law of reflection. Okay, so this diagram you have to learn to draw. See, I already told you this AB is the incident wavefront. Already light ray reached over there the point A. There you can make a normal between the at the point of incidence. So the incident light ray make an angle I. Incident light ray reflected light ray is making an angle R. That is the normal drawn here to the wavefront. See, from the B, light has to travel Vt distance from B to A dash. During the time T, from A, light travels from A to B dash. So B dash, A dash is the tangent drawn to the secondary wavelets. So that is the secondary wavefront. So this is the process of reflection. Now we can go for refraction. That is also very simple. See, here S dash is the refracting surface. This is medium 1, this is medium 2. And see, AB is the incident wavefront. These C, B and A are light rays. A, B, C are light rays. See, already the point A, light ray C reached over there, which makes an angle I with the normal drawn according to the ray diagram. See, when you are considering the wavefront is making an angle I here with the separation S dash. Okay, see, from the point A, light ray has to travel in the second medium. And this is a rarer medium. First one is a rarer medium and the second one is a denser medium. This is a rarer medium and this is a denser medium. Okay, so from the light ray B, from the point B, light ray has to travel a distance B A dash with a velocity V1 in the first medium for a time T. See, here velocity is V2 and during the same time T, here A B dash is the distance travel, that is V2 into T. That is V2 into T. Obviously, it is clear that V1T is not equal to V2T because in denser medium velocity is lesser. So V2T is less than V1T. From the diagram also it is very clear V1T is greater than V2T. So you have to make two wavelets. From A you made a wavelet here and from B A dash is another wavelet. So here you can have another wavelet. Here you have another wavelet. So tangent to all these three wavelets are making the secondary wavefront. See, remember, secondary wavefront is lying in the second medium and the first wavefront is lying in the primary primary medium. So since this wavefront is in the second medium, it is a refracted wavefront. That is A dash B dash is the refracted wavefront and see this A dash B dash is the refracted wavefront. A dash B dash is the refracted wavefront and AB is the incident wavefront. Here also you have to show that sin I by sin R is equal to a constant. Sin I by sin R is equal to a constant, where I is the angle of incidence which is made by the incident wavefront with the surface of separation, and see A dash B dash is a refracted wavefront. And refracted wavefront is making an angle R with the separation S dash. So that are incident wavefront and refracted wavefront. How you have made these two wavefronts? Tangent to the wavelets produced from each point on the primary wavefront. Okay, so we have to show that sin I by sin R is a constant. For that, angle CAN equal to I, which is equal to angle BAA dash, that is angle BAA dash, that is both are angle I, that is angle I. Then angle N dash A dash N dash capital A dash, that is N dash capital A dash is the R, which is equal to B dash A dash A. These two angles are R. So sin I by sin R equal to BA dash divided by AA dash, and sine R is equal to AB dash divided by AA dash. It is very clear from the diagram. Opposite side by hypotenuse. So it will remain as BA dash divided by AB dash. Sin I by sin R will become BA dash divided by AB dash. BA dash, what is that? That I have already shown you. BA dash is V1t and AB dash is V2t, the distance. So here this distance is V1t and this distance is V2t. So sin I by sin R will become V1t by V2t. T and T get cancelled, that will become V1 by V2. V1 by V2 will become N2 by N1. That is the refractive index of the second medium with respect to first medium. That is the Snell's law. Snell's law proves, so this diagram follows the Snell's law, so it proves the refraction using wavefronts. Is it clear? So these are the two properties that you have to prove by wave theory of light, reflection and refraction. That only you have to learn from this chapter, Huygens wave theory of light, the first chapter in wave optics. Okay. So we have completed these two properties of light, that is reflection and refraction, or we describe reflection and refraction using the wave nature of light, wave theory of light in terms of wavefronts. So analyze these diagram carefully, and these diagrams are also very important. You have to learn how to make this diagram without proper notations and proper marking of angles and all. Okay, so that's all for today. And one more thing. Numericals from the last two chapters, that is prism, refraction through prism and optical instruments. Numericals from those two chapters I am uploading with this session as in the documents. You can follow and you can go through those numericals and you can solve the rest of the problems in your numerical copy from both those chapters. Okay, simple problems are there. All the problems I have, all the problems you have to solve, and model problems, as usual, model problems I have solved for you, and you can go through that, and similar problems you can solve in your numerical copy. Okay, so prepare for that. So we will meet in the next class.